All right, let's go ahead and get started. Hi, everybody. Hi, everybody. How are you all doing today? Did you get your homeworks done? Were they confusing? How many of you at the end forgot to have a decision? How many of you at the very end of your whole algorithm didn't say decide if one pizza is cheaper than the other and then print out which one was cheaper? How many of y'all forgot? You better fix that. So people commonly do that. Okay. Last time we talked about a whole bunch of things, but there were two things, or maybe one thing, or maybe three things that I told you that was so important I would expect you to know them forever and ever and ever. What were those things? What is an algorithm? Yeah, you remembered. Yes, an ordered series of steps used to perform some task. Why were we talking about algorithms? Why are algorithms important? Because a program is an algorithm that what? And? A computer can execute and? A program, an algorithm expressed in a form that computers can execute and humans can understand. How many of y'all think this is important? Let's try again. How many of y'all think this is important? This is the basis of everything we're doing all semester long. This is super important. We also talked about computers. What do we know about computers? Computers are, but they are stupid. They are stupid very, very fast. So here's what we're going to talk about today. Today we're going to talk a little bit about how computers are stupid, but how they are stupid so incredibly fast. All right? We're going to take a deep and detailed examination of the computer. It's going to be frightening, it's going to be technical, it's going to be scary. All right? But I want you to stay with me. All right? You all ready for this challenge? This is a diagram of a computer. All right, I lied. That isn't really what a computer looks like, right? That's just a rectangle with the word computer stuck in the thing. As I mentioned last class, however, I'm going to lie to you a lot. I'm going to lie to you because a lot of the stuff we're working on is very complex, and I want to lie to hide the complexity. All right? Now, these lights are pulsing. I'm glad I'm not epileptic or something. That would be bad. There we go. I'm going to lie to you to hide complexity. You're going to get the complexity eventually. If you keep learning computer science, you're going to get there. But right now, I don't want to dump so much stuff on you that I break your will to live. All right? And your roommates find you curled up in a ball crying in the closet or something like that because you're so frightened of what's going on. But here's the deal. While I lie to you, I'm all going to lie to you for a little while at a time. And later I will reveal my lie and I will tell you the truth behind the lie. And I am never ever going to grade you on the truth if it's something that I've lied to you about. Okay, I'm not going to lie to you and be like, it works like this, and then you're going to write the exam or something, and I'll be like, ha ha ha, I got you. It really doesn't work like that, and you should have known. All right? So, going back to what we were talking about, this is a computer, right? This is actually a little bit too simple for our purposes, so let's actually look at a pretty simple model of a computer. This is a computer. As far as we are concerned for this class, this is a computer. It has a few different parts. CPU, it's got some RAM, it's got a disk, it's got some screen we can output stuff on, it's got a keyboard we can bang our fingers on and do input, and all of these things are connected together by what's called the bus. Okay? This is our model of computer. This covers every single thing we need to know for the semester. Now, is most of this stuff familiar to you before? You've probably heard of CPUs before, right? Who makes CPUs? Name a company that makes CPUs. Sure. You've heard of RAM, right? When you talk about computers, how much RAM do you have in your computer? Probably like 4 or 8 gigabytes or something like that, right? You have a disk in there for storing stuff. You probably don't know about the bus, but that doesn't matter. CPU. What is a CPU? What does a CPU do? Is the brain of the computer, and what can the brain of the computer do? What? Math, right? That's all it can do is math. And when we talk about computer doing math, while there is some math it can do, it doesn't do that much. All right, it doesn't do that much. It just does it very, very quickly. What the computer can do is work with RAM. RAM is random access memory. And RAM is the part that holds all the numbers on which to perform math on. The part that holds all the numbers on which we perform math. Well, something like that. But this holds all the data, right? The CPU munges the data, it processes it, it computes it, but the RAM is where it's all stored. And pretty much everything we do in this semester, every time we give the computer an instruction to do something in our program, we're going to be telling it to work with something that's in RAM. Now, the important thing about the RAM and the CPU is that they run on electricity. They require electricity to work. Does your computer always have electricity? No, it doesn't, right? Sometimes electricity goes out. What happens to your computer when the electricity goes out? It turns off. And what happens to everything that was in the CPU and RAM? Bye-bye. It's gone, okay? So if we have a computer and we have everything that's running electricity and sometimes the electricity goes away, that would be bad. So we need something to store the data for when we don't have electricity. And what do we have for that? A disk. So let me tell you a story. When I was young, much younger than you are now, I was in high school. We got a computer. It was $99. It was a TI 994A, a computer that dates back to about 1980 or 81. It was less powerful than the wristwatches that, if anybody has a digital wristwatch, it is less powerful than your wristwatch. And at the time I bought it, I did not have a disk. I plugged it into the wall and I could program it. And if I ever unplugged it or the power went out, I lost my program. I had absolutely no way of saving it. So I had to write everything on paper and type it all back in. Life was tough. You kids have it so easy today. And it was uphill to school both ways and snowing, even in the summer, okay? All right, so we talked about when the electricity goes off, the CPU and RAM lose their data. And we have disks. Disks work on a more permanent basis. Older disks work on magnets. They have a little spinny disk in there that spins really fast, covered with a magnetic material. There's a head moves back and forth and leaves little magnetic dots essentially on the surface of the disk that it can then go back and sense how strong the magnet was. Nowadays we have flash drives or SSDs. These also work off electricity, but they work in such a way that they're able to store electrical charges that won't dissipate over time, and they can be read. All right. The spinning magnetic ones are bigger and cheaper. The SSDs are faster and more expensive. So sometimes you have both. All right, everybody with me so far? This isn't too complex, right? Nobody's going to end up tearing their hair out tonight? We all good? Thumbs up? Okay. This is your class, by the way. Let me just mention, I can stand up here. There's no point in me being here. I could just play a video and go get some coffee and come back in 45 minutes. Feel free to ask me questions as we go along. Please. It's boring for me just to say the same thing every semester. If you're not going to talk, I'll just play the videos from last semester. Yes?
So the disks that are in our computers, are those the ones that store electrical charges that don't dissipate?
How old's your computer? I can't tell. But it might have one or the other. Yeah. Uh-huh. Yeah. My computer has an SSD, but my other laptops have magnetic disks. Right now, we're undergoing a change. You'll have both, right? The thing is that the magnetic disks are huge. I mean, they're gargantuan in the amount of space they can store, and they're cheap. But the SSDs are expensive for the amount of space you get. So new laptops typically have SSDs. So anyway, if you want to look after your class, I can tell you if you want or not. But, all right. So the thing about electricity, the RAM runs on electricity, the CPU runs on electricity. It turns out that it's easy to tell if electricity is on or off. It is more difficult to tell how strong it is. Okay? So if I gave you an electrical device and I told you, figure out if this has electricity on or off or not, you could just lick it, which would not be recommended, but you would learn very quickly whether the electricity was on or off, right? If I asked you how much electricity is coming out of there, what is the voltage, you could lick it and it would hurt, and maybe the varying degrees of hurt could be correlated with voltage. You probably would not want to develop that skill, right? So it's easy to tell if electricity is on or off, but it's hard to tell how strong it is. Everybody with me on that? So when the computer and RAM operate, they essentially don't operate on how strong the voltage is. They just says, is it on or is it off? Which is binary. You've heard of computers. Everybody knows these days that computers use binary to represent numbers. Binary means all the numbers it represents are 0 or 1. 0, electricity is off. 1, electricity is on. Got it? So everything we use is based on this series of electrical impulses. It says 0 or 1. We call these Boolean values so that 0 means something is false and 1 means something is true. Everything in the RAM and CPU and on the disk is 0 and 1. Okay? Now, let's just take a minute and think about back to how numbers work. So here are some numbers that we know. Let's say we had a number that, well, let's just think about how numbers work, right? In the first place, and we use base 10, which is what we're used to, right? The first place is 10 to the 0. 10 to the 0 power is 1. The next place is 10 to the 1. 10 to the 1 is 10. Next is 10 squared, 100. Next is 10 cubed, 1,000, 10,000, and so on. The way we represent numbers is in each of these positions, we say how many things we have. Okay? So if we have 7, 10 to the 1s, we have 7. We have 4, 10 to the first, we have 40. We have 0, 10 to the second, we have 0, 100s, and so on. And you can add these up to get the number. Now this just seems like a crazy exercise because we're used to this. Doesn't this make sense? If you have the number 839,047, that means you have 7 1s, 4 10s, 0 100s, 9 1000s, 3 10,000s, and 8 100,000s. Everybody with me on this? You all seen this before? 5th grade, 6th grade? Something like that? Okay, this is just a refresher. You should see that. Binary numbers work in exactly the same way. Exactly the same way. Except instead of having values of 10, we have values of 2. So the first place, we have digits that represent 2 to the 0. What is 2 to the 0? 1. We have 2 to the first, which is 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh, 2 to the eighth, 2 to the ninth, 2 to the 10th, 2 to the 11th, 2 to the 12th, 4,096. Where was I? 13, 2 to the 13th, 8,196, 92, excuse me. And you can keep going on there. 16,535, 32,000, yada, yada. Okay, so these are the powers of 2. And what we do when we have binary numbers is we say how many of each of these we have. But instead of having 1 to 10 digits, we only have 0 and 1 digits. Does that make sense? So here we have 0, 2 to the 0s, which means we have 0 1s. We have 1 2, 0 4s, 1 8, 1 16, and 0 32s. And to figure out what number this is, we add all of these things up. So 0 1s, a 2, we have a 4, we have an 8, 16. So if we add all that up and put it into base 10 like we're used to, that binary number represents 26. Yes? Let's see, 0 times 4. Oh my God, look over there. All right, there's clearly a mistake on my slides. I don't know why it's crept in there. 0 times 4 equals, how about 0? All right, like we were saying, 0 times 4 is 0. Was that what your question was too back there? There were 2 of you back there. All right, is that still 26? Yes, it is. Okay, sorry. Okay, happy now? Because there was a mistake. I do make mistakes. When I have a bag of candy, which I don't because I ate it all, we're going to Costco this weekend. I'll get more. I normally throw candy to people who catch mistakes. I owe you a piece of candy. Don't let me forget. I can dig around in my bag. I might have an old one in there. Okay. All right. So everybody see how this works, right? Binary numbers work just the same way as base 10 numbers do, except we only have 2 digits. And because we only have 2 digits, we have 0 and 1s, and because we only have 2 digits, each place is a power of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, yada, yada, yada. When you get into computer science, you'll get very good at powers of 2. In fact, computer scientists like powers of 2. Most of them. I'm going to make fun of one of the professors you might meet later, Professor Mark Maloof. He lived in a house that was number 6432, powers of 2 combined together, and he didn't notice. So, all right. So, everybody see how these binary numbers work? Sort of. Yes? All right. Let me just say, now that you know binary, you can say there are 10 types of people in the world, those who can count in binary and those who cannot. What is 10 in binary? Two types of people in the world. All right. So, whether you represent a number in binary or whether you represent it in base 10, they are the same numbers. Any number you represent in base 10, you can represent in base 2. It takes more digits, right? So with just 1 digit, we can represent numbers through 0 from 9. With base 2, with 1 number, we can represent 0 or 1. With 2 numbers, we can do up to 4. With 3 numbers, up to 8. With 4, up to 16. So it takes us more digits to represent in base 2 than in base 10. Does that make sense? Everything on the computer is going to work in binary. Everything works in binary. And we're going to be able to convert between binary and decimal. I'll show you how to do that. When we talk about binary numbers have their own terms. When we talk about a number that's expressed in binary, we have different terms to talk about that number. Each binary digit, each number in a binary number, is called a bit. You all heard the term bit before talking about computers, right? Bits. Each single digit is called a bit. 8 bits together is called a byte. You've probably heard of bytes before because everything about your computer when you buy it is expressed in bytes, megabytes, gigabytes, things like that. So 8 bits is a byte. 4 bits, or half a byte, is called a nibble. Swear to God, I'm not lying to you about this. Feel free to ask me if I'm lying, by the way. Ever. I will tell you if I'm lying or not, but this is absolutely true. This is half a byte is called a nibble. Right? And who said computer geeks have no sense of humor? So, we can also refer to something called a word. And the word is the number of digits that the CPU uses when it does its calculation each step. Now, the reason I haven't said how big a word is, whether it's, 8 bytes or 2 bytes or what bit or a nibble or anything, is because each CPU inside its hardware defines how big the word is. Okay? Each CPU inside the hardware defines how big the word is. Nowadays, most of our computers are 64-bit words. Most computers work on binary numbers that are 64 bits long at a time. If you have an older computer, you might have a CPU that does 32 bits. So most of the laptop and desktop computers we work with today, 64 bits or 32 bits at a time. 2 to the 64th, anybody know how big a number that is? Yeah, it's really big. Remember the numbers that I made you add up yesterday? Those were 64-bit numbers based as bit 10, all those digits. All right, other CPUs, other things that do computation range from 8 bits. And these will be things like small embedded microcontrollers that you'll have in thermostats and watches and stuff like that, up to 128 bits and beyond. How many of you all like playing computer games? Anybody have a special computer game desktop that they use? Any high-end video card? So the video cards that we work with today, the high-end video cards, have 128 or 256-bit processors in them, and they have thousands of them. They're pretty wimpy processors. They can't do very much, and they don't run very fast, but they use a lot of bits at a time. All right. Everybody with me so far? Yes? Questions? Yes, sir. Yeah, so there's a trade-off between how fast the computer can run in terms of operations per second and how many bits it does in one operation. And so the GPUs on video cards are kind of like a special case, but they use a lot of bits. I won't go into how And the reason is I don't know. But if I pretend that we don't have time, you'll think I know and that I'm smart, okay? So, but they work differently. Okay, when we talk about your computer, we measure storage capacity and memory in bytes, in terms of bytes. And when we talk about network speeds, we may talk about bits or bytes. People mix these up all the time. When we talk about memory and storage capacity in bytes, how many bytes do we have in memory in a computer? Who wants to give me a guess, order of magnitude? Hundreds, thousands? You look like you want to answer. Go ahead. What's your name? Yeah, I'm picking on you. Catherine, go ahead. Yeah, and what's giga? Billions, okay? Billions. When we talk about bytes in a computer, we have many of these. Billions of bytes or trillions of bytes. A billion, remember, is a number that's so large humans can't really understand it, and a trillion is a number that's 1,000 times larger than numbers that we can't understand. So it's 1,000 times less understandable or something like that. But we have a lot of these bytes. We have terms that we use to represent bytes for things. Kilobyte is 1,000 bytes. Megabyte is 1,000,000 bytes. Gigabyte is 1,000,000,000 bytes. And terabyte is 1,000,000,000,000 bytes. These are big. Disks these days are terabytes. You might have a disk array that is tens or hundreds of terabytes if you're doing scientific computing. A terabyte, just for comparison, the information on a DVD, a movie, is about 4 gigabytes. So a single terabyte can hold about 250 DVD movies on a single terabyte. And nowadays you can buy 4 terabyte disks for $200. So you can get a single disk that will hold 1,000 HD DVD movies. Sir? I'll tell you the truth in just a second, okay? Yes, this is not really a lie, this is the truth, but there's another way of measuring these things. So here we're measuring these things all the way. Notice that these numbers are powers of 10, right? Powers of 10, 1,000, million, billion, trillion. Sometimes, however, because we are computer scientists and we like not powers of 10, but powers of 2, that's right, we measure things a little bit differently. I don't want to call it a lie, but some people will use kilobytes as base 10 and base 2 interchangeably. There is a formal language to talk about things for powers of 2 that most people do not use. But we have what's called a kibibyte, and B is for binary, kilo binary byte, which is 2 to the 10th. It's actually 1,024. It's bigger than 1,000. So you have a kibibyte, a mebibyte, which is 2 to the 20th. It's more than 1,000,000. 2 to the 30th, which is a gibibyte, and 2 to the 40th, which is a tebibyte. Now, powers of 2 are all going to be bigger than the corresponding powers of 10 by about 2.5%. Okay. And here's the deal. Like when you buy computer equipment, they typically use the binary bytes, kilobytes, but often your operating system, when it formats things, will format them as kebibytes and binary bytes, and so you'll have a little bit of offset between the two. Is that the lie you're referring to? Yeah. So it's just different people measuring. Okay. All right. So everybody happy? We have binary numbers, bits, bytes, nibbles, kilo, mega, gigi, tera. All right. Everybody good with that? All right. I've been talking for almost 20 minutes. Going to take a 1-minute break and play. Stand up, stretch, scream, throw things at other people than me, whatever you like for a minute. So. I'll even turn on the lights. How's that? It feels like a good break, doesn't it? Yes? So sometimes you buy if you buy like a 100 gigabyte drive and you put it in your computer and you format it and you look at how much space, it'll say that you have like 950 megabytes in there. Right. Yeah. 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 It's because there's differences between the measurements. It's super common. People advertise everything in powers of 10 because it seems bigger, right? It's easier if you're not a computer scientist yet, if you don't work in powers of 2. But then what happens is the operating system and the thing does it in powers of 2, and you get this mismatch. And there were like lawsuits over it and stuff in the past. So that's crazy. Yeah, they complain. Yeah, because they're like, I paid for this and I got that. And it's just, people were not very precise in using whether it was kilo or kebi bytes or mebi bytes. They would use the same term for both. So, yeah. All right. Everybody feeling more fresh? Break over? All right. It's got to be hard sitting out there in like the kind of dark and just, it's warm in here. Okay, so the question is, if we have binary numbers and we want to have decimal numbers, how do we do that? Anybody know? Ask Google. Google will do it for you very quickly. All right, sometimes we may have to convert numbers from decimal to binary. We might have to do it ourselves. Here is the official formal way that I'm supposed to teach you, okay? And what you do is you start with the number. Here's 13. The red doesn't show up so well, does it? Here's 13, and we want to figure out what 13 is in binary. What we're going to do is divide it by 2 a number of times. Each time we divide it by 2, we are doing integer division, which means we are not going to be worried about decimals. We're going to be worried about how it divides and what the remainder is. So let's step through this. 13 divided by 2 is 6 with a remainder of, got it? And the answers are right there, right? Should have done sort of fancy animation so you can see. All right, 6 divided by 2 is remainder of. 3 divided by 2 is 1, remainder of 1. 1 divided by 2 is 0 with a remainder of 1. So we're doing it, and then we have 0 left, and now we're done. The question is, how does this tell you the answer of what the number is in binary? Well, here's what we do. Once we have done this, once we've divided by 2, looked at the results in integer, move the result over, divide it by 2, and so on until we get to 0, when we read this column of the remainders, by the way, remainder is called mod in computer science, okay? You're going to be doing a lot of mod in the near future. All right, remainder is mod. You read these in reverse order from bottom to top, and that will tell you what it is. So if we did it correctly, then 13 binary is 1101. Okay, 1101 should be 13 in binary. Is that correct? How many of y'all think it's correct? How many are just guessing because I put these slides together and I wouldn't put wrong things on the slides? Well, let's check and see, because obviously I make mistakes with 4s sometimes. So here's what we do. If we have the number 1101 in binary, we can convert it back to decimal. And the way we do this is we look at each place. The first place is 1 to the what? Which is, so we have 1 times 1. The second place is 2 to the 1, which is 2. We have 0 times 2. The third place is 2 to the 2, which is 1 times 4, to the third, which is 8. So we add these up. 1 times 8 is 8, plus 1 times 4 is 12, plus 0 times 2 is 12, plus 1 times 1 is 13, 13 decimal. So 13 decimal is binary. Yes? Which, the one before the division? This one? It's okay. So in this case, I just picked this binary number randomly. I wasn't converting from decimal to binary here. I just picked a binary number, and then to show how you can add them up and see the value there. Does that make sense? So we're not doing any division. Does that answer your question? If it doesn't, please ask again.
I was just curious about how you know if you're creating a binary number from like a regular number, decimal, I guess.
Uh-huh.
How you know
Which bits to set? Okay, so that's what I was showing you in this other example. Right here. So what we're going to do is we take the number and divide it by 2, write down the remainder, write down what the division is and the remainder is. Does that make sense? And then the next step is we take the thing that we divided by 2 and write it down on the next line. divide it by 2, write down what the division was and what the remainder is. With me so far? Take that down, that 3, divide it by 2, get 1 with a remainder of 1. And then what we do is, it says in red, so it's hard to see, we read these numbers backwards, in backwards order. Okay, so this bottom one will be the leftmost number, second leftmost number, and second rightmost number. And that's how we figure out which bits we're setting as part of this operation. Does that help? Okay. And then we check, and we're good. Now, that's how I'm supposed to teach you how to do it. Okay? Everybody think they can do that? Everybody knows how to divide? Anybody not able to divide in this class? Nobody can divide? Not one person? Who knows how to divide? Whew, man, all right, I was scared for a moment. Okay, so we all know how to divide, right? So we can do it this way. Let me tell you the way computer geeks do it. Somebody shout out a number less than or equal to 64. What was that? 41. Okay, so if I'm doing 41, here's how I'm going to figure out how it goes. The highest power of 2 that's less than 41 is 32, so I get 132. Subtract that from 41, I get 9 left. The highest power of, the highest power less than 62 is 16. There's no 16s because we only have 9. There's an 8, and there's a 1. So I have 100101 is how you do 41. Okay, so you can just, instead of doing the division, you can just do repeated subtraction. Take the number, figure out the highest power of 2 that fits into it, subtract that. That's your leftmost digit. Take the next power of 2. If that doesn't fit, it's a 0. Take the next power of 2. If that doesn't fit, you just subtract all the way down. Okay? That was really fast, wasn't it? 'Cause I'm a geek. I don't have a slide to show this, but I'll turn on the lights for a second and just do it on the board, because this is how people really do it. So the number that was shouted out was 41. And I know that the highest power of 2 that's less than 41 is 32. 41 minus 32 is 9. Okay, so the next power after 32 is 16. There'll be no 16. The next power is 8, and so I have 9 left. Is there an 8 and a 9? Yes, so I subtract that and get 1. So I have 1, 0, 1. Now I have a 1 left. 4, 2, and 1. So these are going to be 0, 0, and there's a 1. So I kind of cheated again and went fast. But essentially you just subtract, and in the end I know it's 1, 0, 1, 0, 0, 1. That's how I convert from binary to decimal. Okay. Did I go way too fast? So the thing about, I'm going to tell you right now the hardest part of the class, teaching this class for me, the hardest part is that everything I'm teaching you is ingrained in my body at a cellular level, because I've been doing it for so long now. And things that seem dramatically easy to me may not be easy. It's just that I've done them so much I think it's easy. So I go fast. And when I go fast, you all sit and look like you're looking now, which is like, and that's when I know that I've probably gone too fast. But you can explicitly say, dude, slow down. What are you doing? Okay, so. Oh, sorry, this was actually a 16. So I'm just doing powers of 2, which I know are 1, 2, 4, 8, 16, 32. So the highest one that fits is 32. So 41 minus 32 gives me 9. So I wrote that over there. But I know there's a 32. 16 is bigger than 9, so I can't subtract a 16. So there's 0 16s. 8 is less than 9, so I can subtract 8. It gives me 1, and I wrote that down there. 4 is bigger than 1, so there's no 4s. 2 is bigger than 1, so there's no 2s. And there is a 1, so 1. So it ends up being 1, 0, 1, 0, 0, 1, just through subtraction. Was that too fast still? Be honest with me. You're paying money. You're paying money to have me do this. And I'm just going to take your money and go home if you don't ask questions. All right. Other questions? 17-second rules in effect. Everybody think they can do this? You're going to. It's going to be on the exam. All right. So let's talk about stuff. So we can convert from a base 10 number to a binary number, right? They represent exactly the same thing. They represent a quantity. And we can represent it either way. They're exactly the same thing. Sometimes when we're talking about binary numbers, we have very, very long binary numbers to keep track of. Anybody here ever heard of encryption? Anybody heard of encrypting things? Encryption takes a key, which is a secret. You keep the key secret, and you can encrypt something. If you want to share the key with your friend so they can decrypt it, that can be a pain. Because binary numbers, long binary numbers that are like 512 bits long or 1024 bits long, are very easy for computers to work with, but they're hard for people. So for example, if I gave you a 1024-bit key and I asked you to read it over the phone to someone, you'd be like 10010100011100, and then you'd lose your place because there's like 1,000 of these things, and after all you'd be like going, I can't keep track, and your friend would read it back to you and it would be bad. Okay, so we don't do that. What we do if we have to communicate a binary number to somebody else is we use a notation that's called hexadecimal, and in short we just say hex. So computer geeks will say, oh, in hex it is, and they will give you a number in hexadecimal. Here's how hexadecimal works. How many digits are there in base 10? How many letters are there in the alphabet? How many characters are there in hexadecimal? 16. Okay, that's a good guess. All right, we have 16 characters, 0 through 9 and A through F. 0 through 9 and A through F. Each one of these characters represents one nibble. How big is a nibble? 4 bits, half a byte. Each hex character represents one nibble, and it looks exactly like this. So, if we know about nibbles, they're 4 bits. Each one of these 4 bits represents a number from 0 at the top, 1, 2, 3, 4, 5, 6, 7, 8, 9. When we get to 10, where we would normally write a 10, in hex we write A. For 11 we write B, 12C, 13D, 14E, and 15F. So hexadecimal, 16 characters or 16 digits that range from 0 to F. And each one also has the same thing, a decimal value from 0 to 15. All of these are the same thing as expressing, same way of expressing a number. Everybody with me on this? You all seen hexadecimal before? Yes? Okay. So here's how we use hexadecimal. We normally don't do math in hexadecimal. We normally don't use it for operations. It is a convenient notation for us when we're talking to each other to represent large strings of bits. Here's how we do it. Say I gave you a long binary number, and this one is not very long. I will tell you, it's actually relatively short. If I gave you this long binary number and I wanted to represent it, instead of saying to you 11011010110011001100110011111111 and having you write that down, you would split it into nibbles. You cut up the binary into chunks of 4, and then you replace each one of the nibbles with its hexadecimal value. Everybody with me so far? And now, when you write that number as hex, you write it as the hexadecimal values, DAC 78E7B. Is that easier than all the ones and zeros that I was setting out? Yes, it is. Way easier. That's why people use hex. Okay. Now, one of the things, though, is that it can be hard to differentiate when you're using hexadecimal from when you're just using normal letters and numbers. So what we do is we will often put, this red is not a good shade, but we'll put this 0x in front of it. This is a notation that's used to mean the number is in hexadecimal. 0x in front of something means that it is hexadecimal. All right, everybody with me? Who's against me? All right. So this is how we write numbers as hex. Now we have another problem. What digits are in binary? What digits do we have? There's only 2, 0 and 1. Do 0 and 1 appear in base 10? Yes, they do. Do 0 and 1 appear in base 16 or hexadecimal? Let's say I gave you a number, 101. What does 101 mean? Is it 101? Is it 9? Is it whatever 101 is in hexadecimal, which I think is 257? You may not know. So sometimes in this class on exams and problems, I will put a subscript next to the number to tell you what base the number is in. So 101 with a 2 means that we're using 2 digits. It's binary. And 101 in binary is actually the decimal value of 5. I'll put a 10 to represent base 10. 10110 is actually 101. And I'll put a base 16 after it to represent its hexadecimal. And if you actually did all the math, you'd find that's 257. I don't expect you to be able to do that. Okay. Everybody good so far? Any questions about differences between binary, decimal, and hexadecimal? Yes, sir.
So the 101 in hexadecimal
Mm-hmm.
is that 1 is representing a nibble. So each of those characters representing a nibble. So that's how you get the 257.
Yes, because what you end up having is, if you convert this into binary, you have 1, 0, 0, 0, 0, 0, 0, 0, 1. And if you actually expand that out, it's 257. They're all just different representations of the same number. Yes?
Why are things always in 4? Like a long piece of binary would always have to be in 4 to convert to hex.
Okay, so the question is, if what happens if you don't have chunks of 4? You put extra zeros at the leftmost side and the highest places to make it 4, because those leftmost zeros don't matter. Does that make sense? So you can just add zeros as far as you want to the leftmost and it doesn't matter, and you split it up that way. Your question?
Couldn't you, instead of like converting it to hex, couldn't you just do it the same way we go from 10 to 2 and all that?
Yes. In the past, I used to teach people, given a hexadecimal number, dividing by 16s and stuff like that. The method works exactly the same way. It's just that we never actually do that. Like, the only stuff we use hex for is really transmitting binary strings around. And so it's just easier to tell you the shortcut way to do it. Does that make sense? So, okay. Other questions? All right, well, if there's no questions, you must be ready to do it. Let's hand out an exercise. Partner, just like we did yesterday, introduce yourself to the person next to you if you haven't before. There's a sheet. They both say binary conversion, but one of them says convert 9310 to binary. Do that side first, and then we'll do the other side. So you have about, once we get all these things handed out. Yeah. Partner exercises. One of you, just like we did yesterday, one of you is going to be the problem solver, one is going to be the talker. And there's 2 problems. One of you do one of you do the other. No reason not to be social. You all are mostly first year, right? Do you all like live together in the same dorm and stuff? New South or something? Don't do that. Yeah. I'll step on it. That's what I'm really afraid of. I yell at my kids. I leave like the iPad on the floor and I'm like, there's a few extras somewhere. Extra sheets somewhere, extras? Right behind you.
How do we know
We'll do that next. I'll show you. I'll show you in a second. We're doing this side first. I'm gonna do, yeah. So you should be working on the one that says convert 93 base 10 to binary, that side. Okay? What? All right, one more minute and then we'll do the first sheet. No, don't go to the back yet. We'll do the back next, yeah. Of course you can ask me questions.
The hex characters back up on the screen.
Oh, no. I'm not going to do that. Mm-mm. I told you not to do that side yet. We'll do that next.
No, but will you tell me what they are for my notes?
And they're in the book. I'll show you how to recreate them in a second, okay? It's really easy. There's like a pattern. You can write it out in like 5 seconds, maybe 10 seconds, depending on how fast you write. Okay. Yeah, the pattern's easy once you see it. Once you see it, you can figure it out really easily. Your notes are wrong is a problem though, so you won't recognize it from that. Yeah. All right, we're going to go ahead and do the first side of the sheet now, the one that says convert 93 base 10 to binary. What brave volunteer wants to talk me through this? Normally I do it for Candy. Again, I ate it all. I'm sorry. Yes. Your math major should be easy, right?
Sure.
Go ahead.
Okay, so I did it where you did that. So I
Okay.
started with 93, and the largest power of 64. I just subtracted 2 from 9.
Okay. So.
Sorry, there's 164 in there. So there are no 32s.
Mm-hmm.
There'd be 116. You subtract those, you get 15. So then in that there would be 1 8. And then there would be 1 4. And 5. There would be 0 2s and 1.
Okay. So what number is this then? What's the binary number?
1 0 1 1 1 0 1.
Yep. 1011101. Okay. So that is 93. Thank you. I'm going to mime throwing candy to you. I owe it to you next time. Okay. All right. Everybody agree with that? Is that what everybody got? Great. Next one. Convert 01100101 to decimal. Who wants to do that one? Sir. Uh-huh. Uh-huh. So, sorry. Let's just do 1 0 1 0. Uh-huh. Okay. Okay. All right, everybody go with that? All right, turn it over, go to the other side. I'm going to show you a quick trick that is not in my slides, okay? And the question is, and I had this before, is if you're on a test and you don't have all the binary stuff at hand, how do you know which nibble represents which character, right? Now, I'm old. I've been doing this for like all of your lifetime, and so I pretty much just know. But there's a way to do this that makes it really easy to create this table if you need to look it up. And here's what you do. You start by writing 0 1 0 1 0 1 0 1 0 1 2 3 4 5 6 7 8 times. Then you write 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0. That can't be right. Let me just check this right. That's right. Oh, thank goodness. Whew, that scared me. I was like, because I shouldn't end with a 0 0. So, okay. So you write that. Next one you do 4 zeros, 4 ones, 4 zeros, 4 ones. Next one you do 8 zeros, 8 ones. And now you have the hex table. And now you write everything 0, 1, 2, 3, 4, 5, 6, 7, 8, A, B, C, D, E, F. And you're done. And on a test or in the world, you can do that in pretty fast. Do you all see the pattern? So the first place, for ones, it's 0, 1. For the second place, it's 2. For the third place, it's 4. For the third place, it's 8. And you can draw the table out really quickly. Okay. Sir? It's no. No is the answer. But that's just the pattern that it works out to be. And when I was doing this in high school, I sort of realized that. Because back in the day, when I was young and had to walk uphill in the snow both ways, even in the summer, when you were doing graphics, you had this little block and you had to put zeros and ones for which pixel you wanted to turn. So I spent a lot of time doing this, and I eventually realized that since I needed hex, I could just do this. But it's easy. All right, so with your partner, go ahead. One of you do one of you do the other. I'm going to erase this so you can do it yourself once. Sir? Uh-huh. You can just start with 1, 0. You don't have to make it nibble aligned. It's called nibble aligned when everything's 4. You don't have to do that. If there's leading zeros, you can omit them. So.
I see the number 34 everywhere. Do you have a number like that?
6.
Yeah, okay.
No, I don't really have a number like that.
Everywhere I go, and it's
I have like a bank app that I log in and it sends me a text message with a random number, and for a while I was convinced that it was putting too many 6s in there.
really.
I was concerned, yes.
I think you should know it's 34.
Uh-huh.
6. So
Yeah, how about that?
it's a thing, I promise.
All right, are we all ready to go over these? These are pretty easy once you have the table, right? Yeah. So the first one, what's the answer to the first one?
0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0.
Yeah, I have no idea what you just said, but it sounds right. That's why we use hex instead of binary, right? And then the other one, what is it? It should be like D3, 4. Whoops, I got messed up. Okay. D3, 4, 6, B. Yeah. All right, everybody good with that? Yes? If there's not enough, so if you're doing something like if I wanted you to convert this number to binary, like that, and you'd be like, split it into 4, you just put some extra zeros in the front if you need to. You can put as many zeros in the front as you need. Okay, does that make sense? Sir? You always add to the leftmost, right? Because these are the higher order digits. If you start putting things down here, each time you add a digit, you're multiplying the number by 2, which would be bad or confusing. So, but if you need to convert from binary to hex and you don't have enough digits, just put zeros on the leftmost side. It's like the difference between, the number 10 and the number 0010, which we don't even say, but it's the same thing. The zeros are implicitly there. All right, everybody good? Questions? All right. Now the question is how much of this you have to do. The answer is you don't always have to do that much of it, but it's handy to be able to do it when you need to, right? Particularly the hex binary stuff. All right. So we've been talking about all these numbers when we really started talking about the computer and how the computer works. So let's get back to talking about the operation of the computer. All right. What we've just talked about is we said the computer can do math. We said the computer does math on numbers, and all the numbers are binary, and now we're able to convert the numbers the computer uses in binary to numbers that we are more comfortable using, right? Everybody good with that? See why we did that? And we're able to convert binary numbers to hexadecimal so that we can communicate them with each other. All right, so let's get back to talking about how the computer works. Here is our highly advanced model of a computer. CPU and RAM, bus communicating with them, and carrying data to the disk and to the screen and the keyboard as well. Okay. By the way, the bus is a lie. There's typically many buses in there. There's a separate bus for communication from CPU to RAM. Typically, there's a separate bus to get to disk. There's a USB bus, Universal Serial Bus. USB you've heard of as a type of bus to talk to the screen and other things for the monitor, but we'll just say there's one bus. So we know the computer works, and it works very, very fast. The question is, how does it work very, very fast? For pretty much every operation that the CPU does, it does something like this. First, it gets some number from RAM by saying over the bus, hey, send me this number. If it needs to, it can get another number from RAM saying, hey, send me another number. Both of these are stored temporarily on the CPU. It does some operation on them. It can add them, it can subtract them, it can compare them. It can multiply them, it can divide them, it can do some few other things too, but it performs this operation on the numbers it's got from RAM. When it's done, it puts the result back into RAM. Okay? It puts it back. Now, this last step can be important, but it can also be omitted. There are times when you do calculations that you do not care to store the results. You're just using them temporarily, so you get some numbers, do some computation, and then you're done with it, so you forget about it. There are other times where you take numbers from RAM, you do some operations on them, and when you're done, you know you're going to need that result later, so you explicitly say, I'm going to put it back in RAM. All right? This is pretty much all the computer is capable of. Everything I just talked about there. Taking a number from RAM, doing operations on it, putting it back. That's pretty much all the computer can do. It does this blindingly fast. Your computer CPUs these days are typically running 2 to 3 gigahertz. A gigahertz is 1 billion times a second. Each hertz, it's able to do one of these operations. At least one. Some computers do multiple ones in a single round. So when you're talking about numbers and how fast things can happen, your CPU is doing billions of these a second. Okay? Billions. It's very fast. All right. Everybody good with that? We're working with things. Every single we're going to get a number from RAM, do something on it, and if we need to, put it back. All right? That's important. It seems simple, but it's important. The whole language is based pretty much around that. RAM, when we talk about RAM, RAM has its own structure. That is, it's not just a box you can shove things into and you reach in there blindly hoping to pull something out later and they're all rattling around loose in the meantime. Typically, RAM these days looks something like this. Each slot in RAM is 1 word wide. Remember, word is the unit, a chunk of size that your CPU operates in. Typically these days we're working in 64-bit words. So what memory is a bunch of cells, billions of these, billions and billions of these, each one of which can store a 64-bit number. Now the thing about these things is that each one of these cells has an address. And the address is literally just a number from 0 to however many cells of these you have, which is typically in billions. Billions and billions of these things. Each one of these things has an address. Traditionally, we represent the address as a hexadecimal number. Okay? And it's just because otherwise you're looking at numbers that are like billions and billions big. But typically when we look at addresses, they're hexadecimal numbers. Remember, binary, decimal, hexadecimal all mean the same thing. They are just representation of some integer number. Okay? Everybody good with that? So we have billions of these cells numbered from 0 up to however many billion we have. Okay? Yes? Every time the CPU goes to access something from memory, it is accessing a value in one of these boxes. So if we say, hey, get this number to add it up, it goes to memory and it looks in one of those boxes and it takes that number and moves it over to the CPU to operate on. Everything we work with is going to be in one of these boxes. Okay? All right, so this is important. This is all important. This is CPU takes numbers out of RAM, does something with them if it needs to, put them back in RAM. RAM is a whole bunch of little boxes. They have numbers with them that are addresses, and we'll see later we can put names on each one of these as well, which will be very convenient to us. So, all right, that is everything we need to know about how the computer works. Are you all good with that? Any questions? Does it seem pretty straightforward so far? Okay, it is. It is. Computers are dumb. They are dumb very fast. They can do very little, but they can do it so fast that they give us this incredible illusion that they are smart if we write good software. All right, so we've talked about everything so far except what the whole subject of this class is. We've talked about algorithms. We've represented them as a flowchart and as an outline. You did an assignment that had an outline format. We've talked about how computer work. Now I cannot put off the inevitable. We have to move on and start looking at C++, the thing that you've all come here for. What we're going to do is I'm going to show you the C++ code that is exactly the same as we used in the flowchart and outline format, which is start, input a number, decide if it's even or odd, output whether it's even or odd. This was the algorithm that we did yesterday to decide this. We had start, tell me a number. What I didn't do yesterday in class was give that a name. You all should have called this something like, you know, pizza diameter or radius or square side or something. Most of these will have a name. Divide the number by 2. Is the remainder 1? If so, output odd. Otherwise, output even, and then stop. Anybody ever seen C++ code before? A little bit? All right. So this algorithm, the same algorithm in C++, looks exactly like this. Okay. Exactly like this. So from the top down, I'll just read through this. Pound include using namespace pound include IO stream using namespace standard. Int main int input equals 0, int remainder equals 0, cn angle input. Remainder equals input mod 2. If remainder equals 0, cout even, else cout odd, return 0. How many of y'all are frightened now? Yeah, it's intimidating, isn't it? It's intimidating. But the only reason it's intimidated is because this is the first time you're seeing it. And I'm going to show you that you actually already know a lot of the pieces of this. So let's look at this. So start, the part in red up there, that's the piece of the algorithm we're used to. Here is the equivalent of start in C++. That portion that says pound include IO stream using namespace standard, int main, open close parentheses, open curly brackets, is the equivalent of start. Just like that. As we go through the course, of course, I will tell you more in detail what all these things are doing. But for right now, when you see this stuff, that is where you start. Everybody good with that? Is it less intimidating now? We just took a giant chunk out of it. Man. Tough crowd. Okay, I'm going to have to work on that. Just like we have start, we have stop. We might as well skip the stuff in the middle and go to the easy part. Stop, return 0, and then the curly bracket that closes that matches the curly bracket that opens the start up at the top is stop. This part down here, return 0, is stop. When you reach the return 0, your program will end. Everybody with me so far? Congratulations, I have given you every piece you need to do to write the shortest possible program in C++. An algorithm that just starts and stops. What do you think that will look like? Pound include IO stream using namespace standard, int main return 0, nothing. Start, this part from here up is start, this part from there down is stop. Congratulations. You can now write a C++ program that is a legitimate C++ program that does nothing. As we go on through the semester, your programs will be able to do more and more, okay? All right, who's with me? Who's against me? That's how I was troublemaker. I have a question, or you're against me? Okay, so the question is, why do we have after this curly bracket a space and the return 0 and then another line? And the answer is, the question is, does it have to be that way? And the answer is no. Here's the deal. The computer does not care about returns. The computer does not care if we have one line after the other stacked on top or one line across the screen that is 8 miles long. The computer does not care. Who cares? People, right? Program is an algorithm that the computer can execute and people can understand. We format our code in a way that aids the understanding of people. Does that make sense? So if you've programmed before, you could put all this on one line. It would work just fine. Everybody who read your code would hate you. To be honest, is what happens. Okay. All right, so everybody's good with start and stop, right? Yes? All right, so the next step of our algorithm was this input, the tell me a number portion. And here is where we have to get a little bit more specific in terms of our algorithm to do things in C++. What did I say that one of the important things about an algorithm was? An algorithm is a series of steps, an ordered series of steps that's used to accomplish some task. And when you express the algorithm, you have to express it in a way that the entity that's going to run it is going to understand, right? So when we express our algorithms in C++, we have to express it in a way that the computer can understand. So the input tell me a number part, we need to do something before that. And here's what we need to do. These lines in red are what are called variable declarations. Variable declarations. Remember, the computer can take a number from memory, do something with it, and put it back. The variable declarations allow us to tell the computer ahead of time, hey, we're going to need a box or two out of memory to use. We're going to need a box of memory out of to use. So what we're saying is we need this box called input, and we need a box called remainder because we're going to be working with those two things. Okay, and I've gotten ahead of my slides. These are called variable declarations, and they are how we tell the computer to use the memory. Computer's dumb, the computer's dumb fast. All it can do is take things from memory, do operations, perhaps put them back. So when we declare a variable, we are telling the computer to choose a spot in memory to hold a value for us so that we can use it for something a little bit later. Everybody good with that? Right? Makes sense? Computer's dumb, it's dumb fast. All it can do is get things from memory and put it back. We have to tell it what we're going to be using the memory for. So we do a variable declaration, which we'll talk more about. When you declare a variable, you do three things, possibly three things. You give a name, and the name is what you as the programmer are going to be referring to that box as. The computer works off of addresses, right? But you don't want to have to remember 0F37C is where you store the input. So we have this ability to give things names. You have to give it a type, and the type says inside that box what that number represents. And the reason for that, we'll see in just a moment, okay? And if you want, you can say equals something, and the equal says what value to put in there. So a variable declaration has 2 or 3 parts. It's got a type, it's got a name, and if you want, you can assign it a value at the same time using the equal sign. So what this line of code says is int input. We're going to have a variable named input. It's going to be equal to 0. What the computer says is, oh, I better go over here and find an empty box. I will put a label next to that called input, so I know what the name of that box is. I'll put a type next to it, int, so I know it's a whole number integer. And any time in the future when the program says, hey, input, it'll go, oh, this box named input. I do the same thing for reminder. I say reminder equals 0. What it does is the computer says, oh, I need a box named reminder. I'll find an empty box. I'll put reminder next to it. I'll put a 0 in that box, and I'll remember that it's an integer or a whole number. Yes? So the question is we have types, and the question is, why do we have types? Well, here's the deal. Everything in there is just zeros and ones, right? Everything in there is just zeros and ones. We've seen that the way we talk about binary numbers, that zeros and ones can represent an integer value, a whole number. But is everything that we want to compute a whole number? How would you store pi as a whole number? You can't. How would you store the word pi, P-I-E, as a number? Well, we'll figure that way out. So here's the deal. Every time that we store something in memory, we have to tell the computer and the compiler in particular how we are interpreting that number. We have to say whether we mean for it to be, and these are the common types, an int, which is an integer, a float, which is a decimal floating point number, a char, which is short for character, and character means a single letter or digit, like you and I would speak, like A through B and period and parenthesis and stuff like that. And bool is a Boolean type. When we talked about bool earlier, what does a Boolean type have in it? True or false, right? 0 and 1. You have a question, sir, or are you answering my question? So these are the basic data types that we have to work with. Every time we declare a variable and we reserve a box in memory, we're going to tell it whether it's an int, char, float, or bool. These are known as the basic data types. We'll see others later on. Yes, ma'am. A floating point number, so an integer number is a number that doesn't have a decimal, and a floating point number is a number that does have a decimal. And it's called floating point. Anyway, just because it is. All right, everybody good on that? So when we write our program, we're going to say, hey, grab a box in memory, interpret the box this way, and use this name when I refer to it. So when we get to input, we say input, tell me a number. We can only actually do the input after we've told it where to put it. So we've done the step where we declared the variables, and now we use the cin angle into input. And as we'll see later, cin angle reads from the keyboard. If somebody types something on the keyboard, it copies the value that's typed on the keyboard and stores it in input. What is input? It's a variable, and we know that a variable is what? A box somewhere in memory, right? So going back to our flowchart, it looked like this, cin angle input. We're actually inputting something. And what's really happening with that cin angle is it's reading some stuff from the keyboard, getting the numeric value, and sticking it in memory. And later, anytime we say input, the computer will go, oh, there's a box over there named input. They must mean the stuff stored in that box. All right. We don't have time to finish this today. I will stop one moment and take questions. And then tomorrow we will pick up and get on to the exciting act of division. You are like the hardest, most quiet computer science class ever. I'm going to have to cry or something. So, yes?
When you give a name to something,
yep.
Doesn't that also have to be like stored somewhere?
Yes.
We're not talking about that?
Magic. That part's magic. That just happens magically. So, yes. The names are also stored somewhere, but that's magic. The compiler is the program that converts your C++ into computer code, takes care of the keeping of track of what types things are and what their names are for you in the background. Okay, that's part of its job. So. All right, other questions? Let's say Thursday? Hey, one more thing I need to say. I'm glad I stopped early. There is a homework assignment due in 1 week, and it is posted. I haven't put it up on Blackboard yet. Your job for next week is going to be to execute that flow chart that we showed last time of how to edit and compile a program. You're going to have an account on a machine named CS class, and it's a server that lives in a closet in Maryland, and you're going to have to type your code in and submit it. We're going to give you the program to type in so you don't have to do the algorithm yourself, and you're done. So anyway, it's only going to take you like an hour if all goes well, so you can take a look at it over the weekend, bring in questions on Tuesday. The one thing about it is I haven't set up all the accounts on the server yet, so you may not be able to do it for a day or two. Okay, I'll try and get those set up this afternoon now that I added people in. Thank you. Have a good weekend.